Hey, John here. Let's talk about sequential circuits. To me, this is the epitome of a sequential circuit. When you take a circuit and you express it in its most fundamental gates, and by that I mean each gate representing only one of the 16 basic Boolean operations that are possible with two inputs, such as the NAND gate. And you look at this circuit, you can see that the gates, at least one of the gates in a sequential circuit, will have its output, like this gate here, we say a U11A. It has an output that we're calling Q over here. And we can see as drawn, that output comes around here, goes into an input of U11B, whose output here, which we're going to call Q bar. You can see the little bar on top of the Q. That output comes back around like this and back into U11A. So we can say that the circuit here has at least one gate, in fact, both of these gates, have its output fed back, in this case indirectly, to its own input. So the value of Q depends on the value of Q. All right, now that's kind of strange, taken literally and in the most, simplistic or naive perspective of this thing. So let's take a slight detour here and put some perspective on this. We may have all heard of a guy named Albert Einstein at one point. Well, he observed that nothing can go faster than the speed of light. No thing can go faster than the speed of light. And the speed of light is a finite speed. It's not infinite. You go in the living room, you turn on the lamp or something. How long does it take the light to get your eyes after you click the switch on? Well, you might say, oh, it's instantaneous. No, it's not instantaneous. It turns out light moves approximately 1 foot or 30 centimeters in 1 nanosecond, which is 1/billionth of a second. That's a very finite distance. Especially if you think about, you go buy a PC. How fast is your CPU? Oh, you'd laugh. Oh, I have a 1 gigahertz CPU. Oh, that's terrible. That's slow. In today's terms, right? Well, what's the period of the clock that ticks inside that CPU? That's 1 nanosecond. So that means if you had a 1 gigahertz CPU and there was a wire that came out of that CPU or your computer, that clock would tick twice before some signal or a light bulb goes on and shines out of it, before somebody who's only 1 foot away from that PC would see that has happened. All right? So those of you with a 5 gigahertz CPU, what that means is you're only dealing with, 1/5 of, you're dealing with 6 centimeters is the distance that something can react to the CPU clock before the clock ticks twice. All right. Now, so what am I on all this about? Well, electronics, as the name suggests, has to do with electrons, okay, which is part of an atom. Atoms have mass, electrons have mass, therefore it's a thing. We now know why that if a clock is ticking and there's an electrical signal that comes away from it, it's only going to go so far in so much time. And that's key to understanding this circuit, okay? So that digression has to do with how do you interpret this thing, okay? We say that the value of Q does not depend on Q, all right, because these gates are made up of silicon and other chemicals. And a binary 1 is represented by, oddly enough, a shortage of electrons, usually. And a binary 0 is represented by a surplus of electrons in any one area, like where this wire is coming out of the, silicon and other chemical thingies that make up these gates, right? So how long then does it take if the output of this gate, U11A, this little number here says it's called pin 3. This thing here is the actual name of this. You could go out and buy these gates. This is called a 74LS00. I drew this with an actual CAD tool. I'm sorry about the extra notation in here, but that's what that means if you're interested. The question becomes, how long does it take if this gate decides, hey, I need to make a 1 over here? What does it do? Well, what it does is it gets rid of all the surplus of electrons. It gets rid of them all. How long does that take? Well, it takes however long it takes to get rid of them all, to draw them in off this wire and throw them away, so to speak. Well, because they can't move faster than the speed of light, that takes time. So what do we do then? We say that Q now, because this gate here calculates the value of Q, it depends on what Q was. Not what it is, but what it was. Granted, only moments ago, less than nanoseconds ago, but it doesn't matter. This is not instantaneous, all right? Just due to the laws of physics, and thank your friend Einstein for explaining how that all works. So it is this instantaneous, tiny little amount of time, this little teeny delay that is critical in order to understand these circuits, all right? So let's look and see how this thing actually works. Let's trace this operation of this circuit over the course of time, right? So time now is a component here. So what do we already know about sequential circuits? One, you have these feeding back things going on in the circuit that are explicitly disallowed in purely combinational circuits. And two, due to this feedback and the fact that it takes time to flow through here, time is now part of the equation. So let's look at how this thing acts over the course of time. So down here, let's keep track. Let's say at time t0, we have what? Let's say this S bar and the R bar inputs to this circuit are both 0. All right. What then is the value of these guys at this time? Well, I chose these carefully because, as you'll see, it turns out we can actually give you an answer. Because since these will depend on what they used to be, how do we start? Okay. You start by carefully backtracking through the schematic. Once you recognize what these are, you pick strategically, all right? So I'm going to do that right now. So let's say that S bar equals 0 and R bar equals 0. So small time later, these gates will react and output something, right? Well, we know, because I chose 0 here, this is a NAND function, the output must be a 1. Because one of the inputs or more is 0, right? Anything ANDed with 0 is 0. Therefore, it gets inverted and becomes a 1. NANDed 0, NANDed with X. No matter what this is, this has to be a 1, all right? So we'll say that Q at that time equals 1. And the same thing happens with R bar. Again, we chose carefully. 0 NANDed with anything must be 1. Q bar now equals 1. Now that we know what these are, we can kind of come around here and say, well, would that have changed anything? No, because 0 NANDed with anything, which we now know would be 1, it would become 1, is still 1. Same thing here. This becomes known. It's a 1. Okay, great. 0 NANDed with something unknown is a 1. 0 with something known is also a 1, all right? So this thing is stable in this condition. I don't know if that's readable. I'm trying to look at a monitor over here. Maybe you might have to not watch this on the smallest Apple Watch, maybe, to read this. Sorry about that. All right, so at time t0, as long as S bar is 0 and R bar is 0, we know that either Q is 1 and Q bar is 1, or they become 1 in short order during this period of time, or at, as a result of these inputs, okay? So let's say now at time t1, S bar becomes what? A 1, let's say. R bar stays as 0. Let's only change one thing at a time to make our lives sane and easy to understand. Okay, so what happens then, right? Well, S bar was a 0. Now it becomes a 1, and we now have a 1 and a 1 here. And 1 NANDed with 1 is 0. So now we say Q has to become 0 in reaction to this, right? Sometimes this is called a stimulus. Something changed in the world, and then there was a reaction. Okay, so at time t1, we say that Q will fall from a 1 to a 0. Okay? 1 is greater than 0. 1 is, sometimes we call this high and low, and so on. All right? Now, what happens to Q, this guy over here, right? Something changed, so when we got to evaluate them both, right? Well, if this thing becomes a 0, it used to be a 1, and R bar is 0, it's still 0 NANDed with anything is always a 1, so that stays a 1, and that was 1 before, it's 1 now, and S bar is a 1, so this thing stops changing at this point, right? It acquiesces, it reaches what we call a quiescent state. That's the word right there. This is used in electronics to represent a point in a circuit or a system that becomes stable. Right? It stops moving. All right? Anyway, it reaches a quiescent state at that point. So let's say at time t2, let's raise R bar from a 0 to a 1 as well. So leave S bar at a 1, only change one thing at a time. R bar now becomes a 1. What's going to happen? Well, R bar is NANDed with Q. Q is currently a 0, right? So we can say that anything NANDed with a 0 is still, what? It's going to become a 1, right? Okay. Hopefully it'll stay that way, right? So it stays 1, hasn't changed. We changed R bar, and Q bar did not change. Well, that's nice, because we know that S bar didn't change either, and S bar is a 1, and because Q bar was a 1 and still is a 1, that this will stay a 0. All right, and again, it reaches a quiescent state because this 0 down here was there before. This 0 NANDed with this new value 1 is still 1, and this thing becomes stable again. Great. So far, so good. Now what happens? Let's say at time t3, this bar becomes 0 again. R bar stays at 1. Now what happens? Well, S bar was a 1, and it's NANDed with Q bar, which was a 1. So we have a 0 NANDed with a 1, which must be 1. So what happens here is Q must then change to a 1. Okay, and if Q is a 1 down here, and R bar is a 1, this must become a 0, right? Because 1 NANDed with 1 must be 0. And because Q bar just changed from a 1 to a 0, we need to count back up and see if it did anything over here, right? Well, S bar, we just changed it to a 0. Anything NANDed with 0 is a 1. So this guy down here became 0. So 0 NANDed with 0, that's still a 1. Again, we reach this quiescent state here, and we're stable. Look what happened here. Let me change colors so I don't get too messy with my beautiful handwriting here. Right? Look what is going on here. Both of these signals were 1s. I made one and only one of them a 0. And you can say that Q flipped to a 1, and at the same time, or thereabouts, and as a result of this same stimulus, Q changed from a 0 to a 1, and Q bar changed from a 1 to a 0. This is actually why we call these signals this way. All right, we name them such that under normal circumstances, these two signals will always be the opposite. All right, as we will see, this is a case here that we don't do this. You can, and it will react this way, but what we do is this circuit, as we will see, a little foreshadowing here, that we do everything we can to never allow this to happen. Okay, as a result of disallowing this from happening, everything else is predictable. If you do this, you can end up with a weird situation. Quite as evidenced by the fact that if you call something Q and another thing Q bar, and they don't represent the complement of each other, this should suggest that something bad has happened or that we've misnamed it. Okay, you can misname things and confuse people, but this really is what you want to name these, and this is normally what we call a disallowed state. Okay, so let's continue this a little bit. If then S bar becomes 1, R bar stays 1 at time t4, now what happens? Well, what do we got here? So S bar was a 0, and Q bar became 0 in this previous state. When we raise S bar up to a 1, there's still a 0 down here, which means the output still is a 1. Oops, that's not right. Q equals 1. Hard for me to write and talk at the same time for some reason. So this is a no change, okay? And because Q is a 1, it was before anyway, and 1 NANDed with 1 must be a 0. This Q bar is and continues to be a 0. So this turns out the outputs didn't change this time as a result of S becoming, or S bar, I should say, becoming a 1, right? So what happens here? This is the nature of this circuit. This is a memory, okay? This is how we build memory, what's technically called static memory, all right? As opposed to dynamic memory, and we'll talk a little bit about that later on in some other discussion. But the notion of memory, what is it remembering, okay? What this thing does is it remembers which of the S bar or R bar was most recently set to 0. Look what's happening down here. If S bar and R bar are like this, R bar was 0 here, what happened? When S bar is high and R bar is low, Q becomes 0 no matter what. Right? Look what's going on here. We'd have to do some more scenarios. We'll draw out some more scenarios over time to show that in more detail. But what will happen is that no matter what the state is over here, if R bar is 0, and S bar is a 1, you can actually work this out in your head at this point, right? If S bar is a 1 and it's being NANDed with an unknown, you can't tell me what this is going to be. It would be indeterminate, okay? But if R bar is a 0, it doesn't matter what this input over here is. Q bar over here must be 1. At that point in time, you can tell what this other previously indeterminate value was. Now you can calculate what Q should become at that time because you now have a known and here, and these are both known. And if S bar is a 1 and Q bar becomes 1 no matter what, which it has to because of this, we have 1 NANDed with 1, which means Q must then become 0. So this might, jump around a little bit while it's trying to figure out what to do because the only known at that time is the output of this gate, right? This thing could jump around and jiggle a little bit, but it will become this no matter what, all right? Starting here, you have enough knowns to just work from left to right. If you don't start here in this disallowed state, and because it's disallowed, we'll never let us do this again, right? we start out by saying, I don't know what it is, but I can observe that regardless of what it was, this must become true and become the new quiescent state of this circuit, right? So as we go along here, Q remembers which one of these was 0 most recently. That's what it is. If R stands for reset, the bar over it means that these signals are what I like to call active low. That's a very common phrasing for this thing. This signal is active. It becomes meaningful or true. This is inverted, okay? R bar. When R becomes true, we want to put a zero. To reset, as we say, this circuit, you need to put a 0 on R, not R bar, I should say, not a 1. Okay, that's why we put a bar on there. So if the reset becomes 0, we reset Q. Okay, later on, if we're neither setting nor resetting, it simply stays in its current state. It remembered that it saw R bar go to 0 in its recent history, okay? If then S bar becomes 0, and again, while R bar stays high, do not go in the disallowed state, it will remember that it was set. S stands for set in recent history. Most recent one of these to become 0 was the set, so it set Q to 1 and Q bar becomes 0. Again, they become 1 and 1 after that, and it stays in that state. So this is why time is important. Look what's going on here. I got S bar 1, R bar 1. In a combinational circuit, this situation would have the same output because it had the same input. But it's not a combinational. This is sequential, all right? Which means just because I know what the inputs are now, I don't necessarily know what the outputs must be because I have to know what happened before this point in time. Okay? Before this point in time, R bar was the most recent one to be 0. Therefore, we have this output. And this time, when they're both 1s, S bar was the most recent thing to become 0, and therefore the Q and Q bar have these different values. Okay? Timing is everything on a sequential circuit. So all those diagrams out over the course of time make this hard to understand and hard to read, right? This circuit as a whole, by the way, is called an RS latch. Some people call it an SR latch. It doesn't really matter. These letters here refer to what you're doing with it. It has a set and a reset input, okay? The word latch and flip-flop kind of are interchangeable. When I first learned this stuff some years ago, I never differentiated, no one differentiated between what a latch is and a flip-flop is. They were just interchangeably used. And I bring this up because recent publications, as indicated by Wikipedia, mind you, I've found the same thing. All of a sudden, people have started saying that latches have certain attributes that are unique and different than a flip-flop, okay? That is probably technically not true. I will try, however, I went through my notes recently to make my use of the word latch match the more recent publications in this matter, and my use of flip-flop also match. I was taught that this is a flip-flop, and yet today people are being taught that this is a latch. I'm going to try and shy away from assigning mandatory meaning to these two words in this tutorial, in this class, all right? Because it's just not a good idea. There's too many things that will conflict in various publications. So just understand that is a weirdness thing that's happening out in the world, and we can thank someone for creating a new trend that doesn't make sense. Like that's never happened before, okay? Anyway, let's call this a latch. Some people call it a flip-flop, and the word flip-flop has to do with the fact that these things flip and flop their values back and forth, all right? The word latch, on the other hand, is used to represent that the output here latches onto the input, All right, as you can see, that's what's happening here, right? The memory latches onto history in some way and can tell you what has happened prior to the current point in time. Provided, mind you, that you didn't do something you're not supposed to do, like set both of these to 0 at the same time. Okay. If you don't understand that quite yet, set them both to 0 and then set them both back to 1 at the exact instant in time. You'll see that these things are both, would both be 1s at that point, and they'd both try to become 0 then at a point, and then it would oscillate back and forth and create an indeterminate situation. That's why we disallow both of these to become 0 at the same time. All right, we don't really need to dwell on that so much anymore. Now, the point here is that that diagram, the time diagram of it does this, then that, and so on, is difficult. So what is normally done here is we create a kind of a truth table that includes its own history. Okay, look and see what's going on here. When R bar and S bar were both 0 at the same time, we just say don't do that. This is an illegal state. Quite often you'll find a data book or something that just says illegal, don't do this. Okay, it turns out, as we showed, if R is 0 and S is 0 at the same time, Q and Q bar will both be 1. Okay? But eventually, one of these two things, if anything changes over the course of time, one of these will become 1 before the other one will. Even if you connect physically a piece of wire between these two things so that they both are hooked up in exactly the same time, go from 0 to 1, they still won't go to 1 at the exact same time, because the exact number of atoms in this wire will be different than the exact number of atoms in this other wire. Therefore, because things take time to jump between all these different atoms and move along, one of these will end up reacting before the other one. It will be a very predictable thing, depending on wire and silicon, the number of atoms in the circuit, stray electromagnetic fields in the room, and so on. It will be such that you won't be able to get them both to go 1 at the same time. And anyway, as fun as it is to contemplate all that, is utterly worthless and pointless. We just simply don't allow anyone to do this. Okay, just don't do it. Okay, so what does this mean then? If R bar is 0 and S bar is a 1, you say that Q becomes I can't see, my PDF here is messed up. It looks like the margins are wrong or something. Anyway, the Q bar and Q values will react to this situation. R bar will reset Q. Q becomes 0. Q bar is not Q, therefore it becomes 1. Whatever it used to be, this is what will happen. When R bar is a 1, S bar is a 0, we say Q has become set, and Q bar becomes the opposite of Q. Okay? When R bar and S bar are both 1s, Q is Q and Q bar is Q bar. We say nothing changes in this state. All right, this is how you draw a truth table that includes the notion of time. Sometimes you'll see a subscript down in here. In a truth table, it might say Q sub T minus 1 and Q bar sub T minus 1 to refer to the fact that Q is what Q was at the prior time. Okay, so there's different notations. I couldn't put subscripts in with this particular CAD tool, so I just did it like this. This is also very common as well. It just means nothing changes at that point in time. Now, to that end, let's talk about what we call a timing diagram. I remember that little chart where we go from left to right and we see all those. Here's time 0 and time 1, and we make these tables of value. It's kind of hard to see what's going on in there, right? So normally when we're dealing with a circuit like this, we want to discuss its behavior over time. We put up what we call a timing diagram or a waveform diagram. Okay, it shows you the value of this signal over the course of time, at time t0 down here, t1, t2, t3, and so on. So for an RS latch, this would be a representative timing diagram. I write down here the Q and Q bar output will change if either of these things, the input signals can change. Probably should have put a bar over these variables in this particular note. However, you know that if R changes, then R bar also changes. All right, so that's, you know, that's not me being too obscure there. All right, you should be able to follow along regardless of that. Okay, so unlike the diagram I worked out before, where we started with both R bar and S bar 0 at the same time, what we did here is I started out with them both 1 at the same time, and we mark the Q and the Q bar as unknown. You'll see we draw high and low at the same time. This is why we call things high and low, because we draw them in these waveform diagrams and timing diagrams. You see them go up and down and up and down and up and down. So let's look at some of the terminology in here. Unknown, it's a gray area, right? All that terminology. This should be intuitively obvious, hopefully, just by looking at it, that we don't know what Q is in these two time windows, right? Time 0 and time 1. Both of these are unknown. However, once we know that R bar becomes 0, we know that no matter what was over here, as we've shown, Q must become 0 in reaction to that. And when R bar goes back high again, this will stay. And it will stay until S bar changes. And when S bar becomes 0 here, Q goes from 0 to high. We say there's a leading edge here. On the falling edge of S bar, we will see a leading edge on Q. And that's what this little blue arrow down here means. We say, look, this edge here on S bar is responsible for causing this leading edge down here on Q. As we showed over here as well, it makes sense now, right? The falling edge on R bar is why this one went down. Okay? This leading edge, this rising edge over here on S bar doesn't do anything. There's nothing interesting that happens as a result of this. The memory of the system is retained, okay? Again, later on, R bar can go low. That falling edge causes this thing to fall back down again. It can go back high. Nothing happens as a result of this. The memory is retained. It saw R bar low most recently between these two. It remembered that. Again, the S bar can go low again and cause it to go back up, and so on. This could happen over the course of time. If they ever, like I said, if you ever allow both reset and set to go low at the same time, that is an illegal situation. We don't allow that to happen. It is an illegal input state. We don't do that. All right, so this is what a timing diagram looks like, a waveform diagram. Same general meaning, same term for the same graph here. If you ever describe a sequential circuit and you want to show what happens over the course of time, this is a much better way of showing it than a huge number of truth tables all listed out at the bottom of the sheet. However, when you first understand something, that turns out to be pretty reasonable. Once you do that, you throw away the overly simplistic, the naive approach, and now it's much easier to see what happens, what your circuit does, how this thing behaves over the course of time. These blue arrows here are called cause-effect arrows, and they show you why this is happening in here. Now, this is a very gratuitous use of these arrows. Normally, you wouldn't even put them on an RS latch because everybody knows, and I'm air quoting, everybody knows how an RS latch works. So this is, like I said, if you look up an RS latch and you look for a timing diagram, this may be the only one where somebody actually puts this many arrows on there because, like I said, this is just a given, a well-known, once you've been told how these things work. You would normally not put quite this many arrows in there. All right, I'm not a PowerPoint guy. This is about as close to PowerPoint as I get. Some text in a file here. So, but this is a lot of new material in one go here. So let's make sure that we're all in sync on what we just discussed here. Sequential circuits always have direct or indirect feedback, okay? You saw that. That's the lines that swoop around from Q back to, R and S and so on. Propagation delay through a gate is always greater than 0 because the speed of light, which is expressed by a lowercase c, is not infinite, okay? And due to chemistry and other things, gates are made using physical things. Therefore, They depend on the speed of light. They can't go infinitely fast. Sequential circuits that are built with gates, I have to say this because nowadays with quantum computers, God knows what will happen tomorrow. But if you build them using gates like we do today, they only work because the propagation delay is greater than 0. And we saw that, or we alluded to it anyway, when the RS Latch. If the RS Latch gates responded instantaneously, there could be situations where we wouldn't necessarily know what would happen. The fact that there's a delay is why those things really work. We cannot always state the output of a sequential circuit without knowing about its history. This is probably the most important thing in here. This is the number one most stark contrast between a combinational circuit and a sequential circuit. In a combinational circuit, you always know the output if you are given the current state of its inputs. In a sequential circuit, you cannot necessarily tell me what the outputs are going to be unless I know its history. As we saw, there are some circumstances with an RS latch where you can tell me the current output without knowing its history, but you cannot always do that, okay? Timing waveform diagrams, I use these two words interchangeably. We can use these diagrams to show the behavior of a sequential circuit over the course of time, which is a lot easier than drawing a large number of little truth tables, I believe anyway. Quite often we will see terminology that kind of get related here. A true is usually a 1, which is usually high on a waveform diagram or a timing diagram. False usually is represented by a 0, which is usually shown by a low signal on a timing diagram. I have to say often, because there are systems that use what we call negative logic, where all of a sudden true is always represented by a 0 and it's always a low line on the timing diagram. I won't do that in this class. If I want to show you something on a timing diagram that is, air quoting now, upside down, so to speak, like R bar, I will show R bar on that timing diagram. It is still 1 when true and high when true. The fact that I put bar over its name means that the negation is happening outside of my timing diagram. All right, the point there is be careful. Somebody might actually draw a timing diagram literally upside down if you wander around on the internet. I won't do that. I find it confusing, so I won't do it. And that kind of goes along with this note down here. Sometimes we find it easier to express the behavior using what I like to call an active low signal. All right, that's not negative logic. It just simply means I have the responsibility to put a bar over the S, and this is another way to do that. When you're using a simplistic text editor that doesn't let you put bars on top of text, this is a very common expression. /S means S with a bar on top of it. This is as close as we can get, right, in a simple ASCII file. And a R bar would look like this. So if I say R bar, I'm still saying R is true when it's 1, when it is high. But R bar, when R is true, R bar is 0, okay? This is still positive logic, okay? When I talk about the people that do it upside down, I'm talking about sometimes people will just say R is true when 0. That is backwards, okay? Again, I only warn you, I go off on this because if you go wander around the internet, you might find that sometimes people do this upside down. I find that very disorienting. So I'll be very strict about this when I talk about these things. Another thing that's massively confusing that I have to talk about is the fact that for some reason, I get up one day and all of a sudden somebody prescribes absolute meaning to the word flip-flop versus latch, where for decades and everyone I've ever talked to and worked with had these two words meant the same thing. In some cases, some people prescribe very specific meaning of latch to a certain subtype of sequential circuit, and a flip-flop to another kind of subtype of sequential circuits. We'll talk about this more as we go along, but just so you understand, if you go wander off I start with the Wikipedia page because they have a whole paragraph in there about this phenomenon. They don't get it. I don't get it. It's a thing. I will do my best in this tutorial to use the word latch and flip-flop when I do in a way that's compatible with these people that decided to try and just all of a sudden prescribe meaning to them. Okay? It doesn't matter, in my opinion, whether you use this word or that word. So, it's okay when we speak to be compatible with people that decided to prescribe meaning to these two words. All right? But as far as I'm concerned, those two words mean the same thing. I will refer to these two subtypes, as you will see as we go along, as edge-sensitive and level-sensitive latches. Okay? I tend not to normally use the word flip-flop, simply because I'm lazy. For the guy that has as many words as I do in these videos, I'm sure you're sleeping by now. For me to want to pull one syllable out and prefer latch over flip-flop to save time, I understand the irony in there, but I'm lazy. I tend to use this word all the time, and I will slip up in these videos. Again, that's why I want to throw all this in here to make sure we all know what the rules are as we go forward. Again, start with the Wikipedia page and read their observation, very compatible with my own, that says, what? Anyway, thanks for watching. I'll see you next time.